Okay, so the first talk will be given by Professor Jinhong Yuan and Professor Ning Hai. So first, let me introduce Professor Jinhong Yuan. So Professor Jinhong Yuan received the bachelor and the PhD degree in electronics engineering from the Beijing Institute of Technology, Beijing, China. He was a research fellow with the School of Electrical Engineering at the University of Sydney, Australia. In 2000, he joined the University of Electrical Engineering and Telecommunications, University of New South Wales, Sydney, where he is currently a professor and the head of the Telecommunication Group, School of Electrical Engineering and Telecommunications. He has published 2 books, 5 book chapters, over 300 articles in telecommunications journals and conference proceedings, and 50 industrial reports. He is a co-inventor of 1 patent on MIMO systems and 2 patents on low-density parity check codes. His current research interests include error control coding and information theory, communication theory, and wireless communications. He has caused 4 Best Paper Awards and 1 Best Poster Award, including the Best Paper Award from the IEEE ICC 2018, the Best Paper Award from IEEE WCNC 2011, the Best Paper Award from the IEEE International Symposium on Wireless Communication Systems in 2007. He has served as the IEEE NSW Chapter Chair for Joint Communication Single Processing Ocean Engineering Chapter during 2011 to 2014. He has served as an associate editor for the IEEE Transactions on Communications during 2012 to 2017. He is serving as an associate editor for the IEEE Transactions on Communications. Okay, and the other speaker is Professor Hai Ning. He received a bachelor degree from Shanghai Jiao Tong University, Shanghai, China in 1993, the master degree from University of Yokosuka, Nishihara, Japan in 2000, and a doctor degree from Osaka Prefecture University, Osaka, Japan in 2005. Since 2000, he has been a research associate with the Graduate School of Engineering, Osaka Prefecture University, where he is currently a professor. His research interests are in single processing for communications, wireless communications, and statistical single processing. Professor Ning was an editor of the IEEE Transactions on Wireless Communications and is currently an editor of the IEEE Transactions on Vehicle Technology. Okay, so before we start, I would like to announce the Q&A rules. So all audience, so please be muted during the seminar, and please do not annotate on your screen because your annotation gonna appear on the shared screen. So please type your questions and send them to the host or co-host. We will connect questions from room and the offsite live broadcasting, and then we're gonna ask the questions to the speaker during the Q&A sessions. Okay, the question will be named and encouraged to ask questions by themselves. Okay, so without further ado, let's welcome Professor Jinhong Yuan and Professor Ning Hai to give us an interesting talk. Okay, so I will stop my screen sharing. Hello, Professor Yuan and Professor Ning, you may start.
Jinhong, you are muted.
Professor Yuan, please unmute yourself. Professor Yuan, can you hear me?
Yes, can you hear me?
Yeah, I can hear you. Yeah, you
good.
May,
thank you.
Yeah, share your screen.
Let me share the screen. Can you see the shared screen?
Yes.
Okay, thank you, Jay, for your kind introduction. First, we would like to thank ISAC ETI for organizing this seminar and your kind invitation. It is a great initiative. It is our honor to share some of our current work and design signal waveforms for ISAC. This work actually has been done by Hai and me during the COVID lockdown for almost 2 years. It was motivated by OTFS, which has beautiful mathematics there. OTFS has inspired us to look at the channel from the delay-Doppler point of view or delay-Doppler plane and consider design transmitter and the receiver algorithms to better couple the transmitted signal with delay-Doppler domain channels. With that, we developed a new modulation waveform, which we call it delay-Doppler plane multi-carrier modulation to follow the conventional way people call it multi-carrier modulation signals. Or if you like, you can also call it the orthogonal delay-Doppler division multiplexing, ODDM. And here we are to share some of our development with all of you here. I'm from University of New South Wales, Sydney, and Hai from Osaka Metropolitan University, Osaka, Japan. Okay, so the key of the talk is trying to introduce multi-carrier modulation MC in DD plane. Before we talk about multi-carrier modulation, we would like to briefly overview of wireless channels or revisit how do we represent a wireless channel in different planes. And also introduce OTFS modulation, see how that motivated us to develop this multi-carrier modulation. Hopefully we have some time to left for some discussions later on. In the last 4 decades, we have seen wireless booming from 1G to 5G. Actually, we enjoy the 5G very high speed data rate transmission. The signal waveforms have been evolved from analog system to digital system, from a narrowband FDMA to narrowband TDMA to wideband CDMA, etc. And if you look at the data rate, actually we have done a lot. I mean, we means in the whole telecommunication industry. The data rate has been jumped from a kilobits per second on the first G to more than gigabits per second. You can think about it, that's 6 magnitude higher than what it was offered in the first generation system. As a physical layer researcher or engineer, what we care about is design transmitter waveforms to support high rate. And one of the difficulty for physical layer channel, for physical layer design is dealing with fading and interference, which ultimately is the nature of the system. We cannot get rid of, we have to deal with it, we have to coexist with this system, that is nature. And conventionally, we have a TDMA, CDMA, multi-carrier CDMA, OFDMA, and MIMO OFDMA. You probably signal is localized the time or the frequency or spreaded like CDMA. It's neither localized in either time or frequency. So the design philosophy has been changed from the first generation, second, third generation. In that case, we are combating channel fading. Look at it as a bad boy or bad guy to be exploiting or embracing this wireless channel fading in our 4G, 5G, which for the benefit of we utilize it to improve the capacity or the throughput of a wireless network. So that has been a lot of changes, provide a modern view of communication system design. Looking forward to the 6G, one of the important application scenario is high mobility. We will have vehicle-to-vehicle communications, high-speed rails, and up to 500 kilometers per hour. I think to provide a high reliability over this high mobility channel is not a trivial thing. I think the current 4G system or FDM service its purpose It works well, but if we have a high mobility communication, we know the orthogonality between the subcarriers probably will be destroyed or affected. So how do we design system to cut with this high mobility is one of the issue. Another thing is the connected AI. I think we talk about the Internet of Things or Internet of Everything or Internet of whatever. And we will have a smart home, smart campus, smart manufacturing or remote surgery. A lot of application requires the network is able to provide both sensing capability and the communication capability. That's how bring us all to this ISAC seminar here. And the interactive, integrated sensing and communication. So one of the questions for physical layer design is there any signal waveform better interacting with wireless channels? What do we mean interacting with wireless channel means? What we mean here is the signal is able to provide a robust and reliable performance against all sorts of distortions or impairments, particularly for this AA selective channel. And more importantly, hopefully it is suitable for ISAC over these AA selective channels. In 2017, there was a seminar paper proposed by Dr. Ronnie Hadani and a bunch of famous people called OTFS. OTFS modulation gave us a new way to look at how do we transmit the signals and modulate the signal in the delay-Doppler plane, then convert it to the time frequency plane. Important issue about this modulation is it can work overlay on the existing 4G, 5G OFDM system, provide reliability over high Doppler fast fading wireless channels. In the last 5 years, a lot of work has been done to understand this new modulation and developing transceiver algorithms associated with the delayed Doppler domain signal processing and the communications, such as channel estimation and the detection and the MIMO system. How do we do DD plane pre-coding? What is the security? How do we do multiple access? A lot of been done in this OTFS modulation. The key idea about OTFS modulation is to explore the underlying property of our DD domain channel, which has nice properties like compact and sparse. So if the OTFS idea is if we can carry the information in the DD domain, we are able to couple with the DD channel better. So the design aim is to try to have a full diversity provided by the DD channel. In the meantime, to have minimum cross interference. So that is the design principle for OTFS. So given conventional multi-carrier modulation, OFDM, on the right-hand side, we have a time frequency plane, this time frequency grid resources. OTFS says, let us map the signal from the DD plane to the TF plane, and your data is carried on the DD plane through a inverse symplectic finite Fourier transform. Actually, you can think about it as two pairs of Fourier transform. You map from the Doppler to time, is inverse Fourier transform, and from delay to frequency, it is a Fourier transform. So as long as you do such a mapping, you can use existing and OFDM modulation signals and to transmit your data. So OTFS waveform, as it uses OFDM underlying modulation structure, so it is orthogonal with respect to TF plane resolution. So your resolution R equal to TF equal to 1. In the initial paper, the OTFS assumes if you have bi-orthogonal robust pulses, you are able to provide a very nice property at your receiver using the existing single type equalizer as what you have in the conventional system. But the reality is such a bi-orthogonal robust pulse does not cannot be realized. So most of the existing work focus on OTFS modulation with rectangular pulses. And as an engineer, we always know rectangular pulses suffer from a high out-of-band emission, which is one of the key tasks if you work on 3GPP or practical system, either for Wi-Fi, 4G, 5G system. As a result, you have a complicated ISI and ICR to deal with it. So when we talk about the modulation, and we probably have to care about going back to the textbook knowledge, and each modulation probably have triplets we have to define. And the first one is we need to know and what is the information bits mapped to what kind of a signal constellation, that is signal mapping. Second one, we need to have a transmitter pulse or filters to regularize your transmitter signal spread, signal energy spread in the time and the frequency. It means you need to know what is your time and the frequency resources to be used. Third one is you need to verify, or we need to verify the time frequency lattice, means which time slot, which subcarriers you are going to use. So that is your T and the F. So that is the triplets we have to specify to design each multi-carrier modulation. Here I say, and the time and the frequency resources is regularized in practical system by the standard or by the base stations. And the pulse has to be designed before we employ the modulation. It is a fundamental element for any modulation, as we typically know, because they regularize our energy spread in the time frequency. On top of that, it is also very important to design the pulses appropriately, because the fact that our propagation and the signal characteristics also, it determines the efficiency, localization, orthogonality of our transmitted signal. So in this talk, motivated by this OTFS modulation, we'll take a different view to look at how we are able to design DD plane multi-carrier modulation. Importantly, to answer the question, are we able to design orthogonal pulses with respect to the DD resolution? The answer is probably at the end of this talk, you probably can find it's positive. Yes, we show that there is a pulses can satisfy this requirement. And we will share with the audience colleagues here. And actually, this kind of a signal is a promising waveform for ISAC. With respect to the DD resolution, what does it come from? To answer this question, I would like to revisit the wireless channel with DD domain representation. I think for any linear time variant channel, we are able to represent it in the time delay domain, time frequency domain, or DD domain, or the Delay-Doppler domain. So this is not new, and this has been answered in our pioneer work, Bellows 1963 work, 63 paper, talk about the system of functions. There's 4 fundamental functions, 4 dual functions there. Now we just here, relevant to what we are dealing with, we probably look at, as we conventional see, our channel can be represented as a time variant impulse response, HT tau. And do a Fourier transform with respect to the tau, we got the time frequency response. And we got the channel representation as the time and the frequency domain. We call the time variant transfer function, HTF. And if we do 2 pairs of Fourier transform, symplectic Fourier transform, from the time frequency domain, we are able to look at the channel in the Delay-Doppler domain. That is called the Delay-Doppler spreading function. And it tells us how many passes there, what is each pass delay, tau p, Doppler nu p, and its amplitude hp. And that has been there since a long time. But what we see from the OTFS is shows us conventional system we're dealing with the channel in the time frequency domain. We look at the time variant transfer function means that we look at the coherence region, means the coherence time, coherence bandwidth, design or communication system, regularize our frame length and the subcarrier spacing, etc. And but what we found is OTFS tells us actually we can look at the channel in the delay-Doppler spreading function, and it has nice properties which I'm going to show you next slide. But from a numeric point of view, we can take a look at a typical example. So if we have a very high speed car 120 kilometers per hour in a highway, and you can work out its coherence region, coherence time. If the car is at 5 gigahertz vehicle speed, vehicle frequency band, you can work out that the coherence time is 2.5 milliseconds typically. That means your channel, your channel HTF remains roughly same over this coherence time. That is how you can estimate your channel and use it in your demodulation detection, etc. But if we look at the delay-Doppler spreading function, at the same frequency, if we have two cars, each at 120 kilometers over highway and running at the opposite direction, we're able to see the channel spreading function remains almost the same at 23 milliseconds. If we look at a car to a pedestrian, in that situation, the stationary time or the channel delay spreading function remains almost constant at 1.5 seconds. That means we are able to see the channel relatively stationary in that period in the delay-Doppler domain, even the channel is changing very fast in the time frequency domain. So what does that tell us? It tells us, and in time frequency domain, the channel is dense and changes quickly, difficult to perform the channel estimation. But if we look at the delay-Doppler domain, the channel is compact and stable. It actually it allows us to accurately and estimate the channel with a low overhead because we don't need to estimate the channel so often. So because the channel is relatively stationary, we can think within that stationary time, the channel is deterministic. So we can use a deterministic delay-Doppler spreading function and to represent this channel. So that is what we usually have, this path-based model. So that is a physical channel. Now we need to model that in our communication system. Now let's take a look at how Barrow and our pioneer also, Staley and Hansel, told us how do we do channel. So our real life channel and the path signals and our system has an essential finite degrees of freedom, which means that we have a finite bandwidth, we have a finite time observation period, we have to deal with our signal transmission and receiving. It turns out to be we do sampling at the receiver side. We have this sampled channel model with combined time and frequency constraint. So we have this channel model, H tau nu, is discrete or sampled channel model. And this sampled channel model has a similar representation as our physical channel. But the one difference is the delay tau p and the nu p are integers because that is what we see at the receiver side and what we can deal with it after we sampling the system. So the delay is sampled due to your sampling rate regularized by your channel bandwidth. Doppler is sampled also with due to your Doppler resolution is due to your frame observation period of time. So we always have this integer delay and the Doppler rather than fractional delay and Doppler, what we see at the receiver side. So with this background, we are able to look at how OTFS modulation works. I hope the speed is all right. Yeah. So the OTFS modulation actually use the multi-carrier modulation as its building block. Before we do multi-carrier modulation, the signal is carried on the DD plane or DD domain. We use 2D orthogonal precode, change the signal from the DD plane or DD domain to TF domain. As long as you are in the TF domain, you can use a multi-carrier modulation to change the signal to the time domain to transmit your signal through antennas. Okay, at the receiver side, you have a multi-carrier demodulation, and then you change the signal from the TF plane to the DD plane, and you do this demodulation and the decoding, etc. So this it is a very general and has very beautiful mathematics here. For example, this 2D orthogonal precode, you can use inverse symplectic finite Fourier transform, ISFT, or you can use Walsh-Hartman transforms. For this multi-carrier modulation, you can use OFDM, or you can also use field bank multi-carrier modulation. The essential point I would like to make is the OTFS reliance is the employed multi-carrier modulation waveform. So that is the key here. So for example, if we use the OFDM modulation as its underlying structure, and we have n time slots, m subcarriers, a typical scenario say for 4G, we have each frame has 14 time slots, n equal to 14, m equal to 1024 subcarriers. So that is your TF plane, okay? And so we have the total length of frame is NT. We have the total bandwidth is m delta f. That is the total, m is the number of subcarriers. So to do OTFS modulation, what we need is we need to change the signal or map the signal from the DD plane to the TF plane. So we use ISFT as the transmitter side, we use the SFFT as a receiver side. Here, what I would like to point out, this ISFT and the inverse FFT is a kind of digital sequence implementation. And they have DD plane and the TF plane has the same, actually are the same planes, just have different resolutions. How do we do demodulation? And here I borrow the slides from E and Viterbo's ICC tutorial 2019. So if we have this delay-Doppler signal, we change the signal from the delay to frequency domain, that is the inverse FFT, from a Doppler domain to the, from delay to frequency domain is FFT, from Doppler to time is inverse FFT. Then as long as we got the time frequency domain signal, we change the signal from frequency domain to the delay domain or time domain, you can call it. That is the inverse FFT. So we got the signal in time domain. So we got that the first OFDM signal, which is red, and the second OFDM is the yellow and the blue third OFDM, and the fourth OFDM signal. We stack it into a frame. Then we add a frame-wise CP at the head. So that is a typical OTFS modulation. So you can think you have n OFDM symbols, but only as the first you have this CP. At the beginning of the frame, you have the CP. And you also see this is directly implementation. You can also see, actually, you can do the signal from the delay to the frequency, that is the FFT. From frequency to delay is the inverse FFT. They cancel each other. So you can directly do the signal from the delay-Doppler to the delay and the time. So what does it mean? Means you take the signal from the Doppler, you do IFFT, directly goes the time domain signal. That is the directly implementation, or some people call it the ISAC transformation. So if we look at this directly implementation point of view, you are actually doing inverse FFT. People familiar with multi-carrier modulation or OFDM, you probably think somehow that is relevant to OFDM. Now let me redraw the same picture as what we drew before. So we have this Doppler and the delay signal. And for the first delay, we have the red signal. For the second delay, we have the blue. What we are doing from the Doppler to time domain transformation is just an inverse FFT. Sorry, looks like I need to charge my battery. Okay, so we need to do an inverse FFT for the red first delay, blue second delay, and the green third delay, then stack them together. So for each one, it looks like a multi-carrier modulation, but that multi-carrier modulation is regularized from the Doppler to the time domain. For different, so we may think about that is similar to OFDM, but here is orthogonal Doppler division. For different multi-carrier modulation, for the first red one and the blue one and green one, looks like they are delay division because they have a different delay. When you stack them together, you have the right-hand side curve here. So there's a very good connection between this OTFS and the conventional OFDM, or in general, multi-carrier modulation. So motivated by this one, and we say in order to be a multi-carrier modulation, we need to have a pulse because the signal need to be helpful. So the question is, how do we design pulse? Is the pulse realizable? And what is the properties for this pulse? So with that one, I stop here. I asked my colleague Hai to talk about the important issue of pulse design. I stop sharing. Hi.
Okay, wait a minute. Can you see it?
Yes.
Okay. Regarding the pulse design in multi-carrier modulation, we have several principles about pulse design. Basically, we need one pulse for one symbol. For example, if you want to transmit MM symbols, you essentially you need MM pulse orthogonal with each other. In practice, we usually use a prototype pulse to generate MM orthogonal pulse. They can be written as this function set. In this function set, we generate GMNT from GT using the time shift according to a time resolution, and frequency shift used by a frequency resolution, F and tau, T and F here. So all these MM pulse construct a function set. On the other hand, we also have joint TF resolution, which if you are familiar with multi-carrier modulation, you can see it's called, sometimes it's called lattice areas. Okay. And another important parameter is symbol period. We have two time parameters, but be careful, the time resolution is not necessarily be the same as the symbol period. Then we can find the core of the multi-carrier modulation is to find a suitable GT given the time resolution T and the frequency solution F. For example, for CP3 OFDM, we have rectangular pulse rectangular prototype pulse to generate MM pulse which are orthogonal with each other. So we have M symbols, and each symbols have N subcarriers. It's an example. For the prototype pulse, sometimes we call prototype filters. It's GT given T and F. And traditionally, these function sets are treated as Willy-Heisenberg or Gable function set. And to design a multi-carrier modulation, we need to find by the orthogonal or orthogonal WH or Gable set. And essentially, we need to find a prototype pulse GT given T and F. For example, the OFDM, we have a rectangular pulse for the joint TF resolution 1, when the symbol interval is the symbol period. This basic concept of pulse design can be found in these two very good tutorial papers. Now, let's look at the DD plane multi-carrier modulation. We recall the principle of modulation is one pulse for one symbols. In OFDM, we have a rectangular pulse here to generate the MN pulse. But for the DD plane, you see this plane, DD plane, the delay is also time. The Doppler is also frequency. So basically, the DD plane is also a TF plane, however, with high resolutions. One may think, how about we use this pulse? It's similar, we can have an orthogonal pulse. However, this tiny pulse violates the uncertainty principle, doesn't exist. So it looks like the DD plane orthogonal pulse doesn't exist. Can we find a DD plane orthogonal pulse? We call this time frequency resolutions representation in DD plane. You see, we have a frequency resolution 1 over NT, and we have a time resolution T over M. In the context of multi-carrier modulation, the inverse of frequency resolution is symbol period, just as I mentioned in last slide. So this small frequency resolution means you have a long symbol period. At the same time, the small time resolution means you have a small symbol interval, which means this small interval will result the M symbols stacked with each other. The DD plane multi-carrier modulation therefore looks like a type of stacked multi-tone SMT modulation. This short symbol interval indicates this signal must be wideband. However, the long symbol period in the conventional knowledge about the multi-carrier modulation, the long symbol period means you are narrowband multi-carrier signals. How can signal be the wideband and narrowband at the same time? So it's like, look, very strange. Now let's look at the implementation of the multi-carrier modulation. This block diagram is a general implementation of multi-carrier modulation with time windowing based transmitter. For transmit X signals, we use IDFT to generate the time domain discrete symbols. Then we use DAC to generate the transmitted symbols times the carriers. Then we multiply by the transmitted pulse to get the transmitted waveform. And finally, we time multiplexing all these M symbols and send it to radio frequency. So all we need is all these things. Look, we need a very special UT here. So what's this UT? And the answer we found, this UT is a pulse chain, which is composed of N root Nyquist pulse. Each root Nyquist pulse is designed for a time interval T over M. And each root Nyquist pulse has a duration 2Q T over M. So this NAT could form a UT. The UT is the DD plane orthogonal pulse. And the ambiguity function, if you want to calculate the ambiguity function of UT, you can find the UT is a delta function on the DD plane with respect to the DD resolution. With this orthogonal pulse, we can say the DD plane multi-carrier modulation as orthogonal delay-Doppler division multiplexing modulations. For example, we have N subcarriers. We have rectangular pulse for conventional OFDM. if we are doing OFDM, we have a rectangular pulse for conventional OFDM. But in ODDM, we use a different pulse to shape the subcarrier. The UT is applied to all these summation of these subcarriers. Then we have a ODDM waveform, can be written as this equation. And you can see the ODDM has a standard multi-carrier modulation format where the information bearing symbols are carried by the pulse. And the pulse is orthogonal with delay and Doppler resolution. On the other hand, the OTFS, you can see the OTFS use a discrete transform, map the information bearing symbols to TF domain, then use the TF domain orthogonal pulse. Therefore, ST is orthogonal with T and 1 over T. They are two different waveforms. In the design of multi-carrier modulation, we usually need to see from the degree of freedom. For example, we have a duration NT and a bandwidth M over T. According to the Loud-Park series, the degree of freedom of these signals is approximately Mn, which means we can transmit Mn symbols using this TF region. On the other hand, for the DD plane, you can see this small region only has DOF1, which means if we are limited inside this small region, we can only transmit one symbol. So it's impossible to have Mn pulse inside these small regions. With this degree of freedom, we can compare the proposed ODDM waveform with existing modulation scheme. For example, we have TDM as a single carrier. We send symbols one by one with a fixed time resolution. Also, we have FDM. We send symbols according to a frequency resolution. Also, we have a conventional OFDM. We send with a T time resolution and frequency resolution 1 over T. And finally, our proposed ODDM. It's like a 2D spreading multi-carrier modulation on the TF plane. However, orthogonal with respect to the delay and Doppler resolution. Then another interesting thing is about this pulse ambiguity function, because it is orthogonal with respect to the delay and the Doppler resolution. You can find the ambiguity function. It's very interesting. For example, if we set M equals 0, we can see the this line. Okay, you have a sector here. So you can see for each Doppler resolution, you see the they are orthogonal. You only have a value here. All the integers resolution place you have 0. The same thing happens if you set the N to 0 and you check the delay resolution. It's also 0. So it's a very interesting ambiguity function. Now with this orthogonal pulse, we can easily derive the DD domain input-output relation because it's just like OFDM. So we can use the receive pulse because it's orthogonal. We can just use the receive pulse is the matched filter of the transmitted pulse. Then the pass delay is integer multiples of T over M, and the pass Doppler is integers multiples of 1 over NT. So we know OFDM with integers timing and frequency offset, you have a really special properties we can use to derive the DD domain IO relations. For example, we have a channel can be written in a matrix G. The G, the elements G, K and L represent the Doppler and delay index. Let's see from the n subcarrier of the M symbols, we can see the GKL will bring an ISAC from the n minus hat k mode Tn subcarriers of the M minus L mode M symbols. And use this relation, we can easily derive the input-output relation in DD domain, where this matrix can given in this form. And this matrix has a block circular-like structures. Jinhong, so let's move my part, please.
Okay. I'm sharing my screen. Can you see here now?
Yes.
Okay, thank you. So I probably, I think Hai has showed very good properties of this modulation, but there's no free lunch. And it looks like everything is quite good, except we see, let me show this one. And we cannot use the conventional OFDM and single tap equalizer because the channel has this delay and Doppler interference introduced merely by the channel. It's not by signal itself. We had to be, so how do we do detection? That is one issue we have to conquer. So there's existing work. People have been talk about all sorts of detection algorithm or equalization algorithms. For example, we can use map detection, but the complexity is to the exponential to the signal cancellation size to the Mn. Mn represents the number of time slots and the number of subcarriers. Or if we use MMSE, it is Mn to the power of 3. Or we can use the message passing, and that is linearly to Mn, also to the number of passes and to the cancellation size. Or we can slightly tweak the transmitted signal. So say, let us say DD domain multi-carrier modulation with 0 padding. We can use some low complexity MRC SRC, means maximum ratio combining successive interference cancellation, or MMSE SRC. And the complexity for MRC is MN L. L is the number of passes, or it is MN L to the power of 3 to MMSE. So that's just manageable from our point of view. So particularly say, if you do MMSE, how do you do it? So you detect the first group of signal by using this matrix. Then you remove the interference from X. You detect X0. You remove the interference. Then you do detect X1, then etc. So with that one, I think the performance, the complexity can, and the performance has a good trade-off. Now we are going to show you some results, just 2 results. First one is we show what is the difference between OTFS and the ODDM in terms of their power spectrum density. And you see this OTFS red one has a severe out of band emission, and ODDM, we use raw factor 0.25. Obviously, you have slightly increased bandwidth, but your OBE is matched quite low, more than 20 dB lower than the OTFS. And we also evaluate the beta rate performance for OTFS and ODDM for different speed. You see they both robust to the Doppler shift. But one thing we can see is that at a high signal to noise ratio, ODDM has a kind of 2 dB performance gain over the OTFS. Okay, so the parameter for this system is for the EVA channel at the carrier frequency 5 gigahertz and etc. You will see here. With that one, I would like to summarize the talk with these 2 nice figures. It's like basically motivated by OTFS, we have shown an example of design practical signal waveforms. And in our personal view, this signal waveform, a multi-carrier delay Doppler plane, has a very nice property. One property is you can see in the in terms of our communication system, and our signal is distributed over the time frequency domain. And how do you see the picture? I mean, the same color representing the same modulated signal situated or distributed. And you can see the signal is distributed over the time and over the frequency. Obviously, you have a time selective fading channel, you are able to explore the frequency diversity. Also, you can have the time diversity on the other around. So this is quite new from our point of view. That's interesting. From a sensing point of view, and as far as we understand, the sensing, people care about the ambiguity function, but because that tells you how accurate you are able to estimate your target speed and the distance, etc. And we saw this orthogonality with respect to the delay and the Doppler is quite nice. People would like to have. So fits the ISAC perspective. So we say it's a nice property, like we have a new modulation, embrace the DD channel property. We have designed the DD plane orthogonal pulse and has potential to provide a high reliability in terms of communication system or good accuracy for sensing system. There are still many open questions, probably we may have in our minds. For example, it does not, I mean, the current design, we show an example, but if you look at it carefully, it does not fit in the existing WH frame-based pulse design principle. So from a theoretical point of view, is there any theory we can explore or develop? We don't know yet. And what is the achievable rate for this ODDM? And can we further reduce the detection capability or complexity? How to explore the properties to meet the sensing objectives? And how do you work with multiple user system? And how do you do resource allocation? And how do you work with MIMO system? And latency probably is an issue. So I think there's quite a lot of other issues, but with that one, we stop here and hope this could intrigue researchers for future development. So the main result is publishing our ICC paper and also trans wireless communication to appear. Here, I would like to particularly thank the ISAC special interest group for the invitation, and thank everyone online to listen to the talk, and also thank our founding bodies and industry partners, particularly our great students, postdocs who contributed to the discussion. We also take the chance to say we have postdoc position, existing postdoc positions in this domain. If you are interested, please contact us. Thank you very much, everyone.
Okay, thank you very much, Professor Yuan and Professor Ming. So I got a couple of questions. So now I would like to ask the speakers. So this one question from Professor Andrew Zhang. Okay, the question is, could you please explain intuitively what is the performance gain of ODDM compared to OTFS? Is it because a reduced ISI with the use of orthogonal pulses, but the signal and the channel in the DD domain is a conventional relationship? How the orthogonality improves such a relationship at the receiver?
Okay, very good question. If we could answer briefly, say, in terms of communication system, this is ODDM and have exactly input-output relation, because when you look at the input-output relation, the signal itself is orthogonal with itself. So whenever you have ISI, that is introduced by the channel. So we're able to use this information specifically in this detection when we use method busing algorithm. But for OTFS, you probably use approximate input-output relation, and because your signal is orthogonal with time frequency, but not the delay Doppler. So you have some approximations. That approximation introduce performance degradations here. Hai, would you like to add something, or that's?
I think it's you answer the questions. It's fine.
Yeah. Thank you.
Okay, thanks. So there's another question from Professor Zilong Liu. And the question is, if we ignore the implementation complexity or backwards compatibility, so are you aware of any pre-coding schemes other than OTFS, which are more effective for certain wireless channels?
Very good question. I think there is a paper. Let me try to answer this first and see how I can add something. And there's a paper talking about, if I go back here, OTFS. There's a paper, I think there are a couple of papers talking about how you do pre-coding. And it's by Zeman's paper. I don't think we cited here, but you can find it later. And they say, as long as you do orthogonal pre-coding here, and you probably achieve the same performance because they are all pre-coding based. They say this OTFS can be considered as a pre-coded OFDM system. So as long as it's orthogonal pre-coding, you probably achieve the same performance. And that is my understanding. And Hai, would you like to add something? Or?
Yes, I think the paper is Dr. Zeman published in 2018 PIMRC. Yeah.
Okay, thanks for the excellent answer. And this other question from Ahmed Bazi. And the question is, why are the multipass components always assumed to be on the G grade or integer multiples? So could they lie in between or not? And okay. Is this like a compressive sensing type approximation? So that's a question.
Okay, very good question. I think in the literature, let me try to answer this one first and see how I want to add something. In the literature, we always say fractional delay and fractional Doppler. I think there could be some concept to be clarified. I would say this: in physical channel, your delay and the Doppler. If we look at this one, the path-based model, there's the tiered tau p and the tiered nu p are all any real numbers. And so they could be any number. There's no grade and for time and frequency or delay Doppler at all, because this is exactly physical channel. But what Bellow and Stella Hansel tells us, whenever at the receiver side, we observe the channel due to we have the limited degree of freedom, basically limited bandwidth and the limited what is called time duration for us to do the signal processing. And we do sampling. After sample, all those off-grid passes will be combined or not combined, somehow combined. And what we see is their combined version on the grid. So for this model we show here is what we see. It is what we model the real physical channel. But what we see is this tau p and the nu p are on the grid. So this model, two different models. One is a real model, another is a modeled, sampled channel model. So whenever we sample this channel model, it is on the grid. Yeah, that is not saying your physical channel is on the grid. Okay, that is the point I would like to make. Hopefully it is clear.
Yes, thank you very much. Thank you. And very interesting talk, by the way.
Okay, thank you.
Okay, so due to time limitation, maybe I will have a final question. So the question is from Jinhong. Okay, so the question is regarding the effective channel in the digital domain. So the question is, could we expect that the ODDM will see a much sparser channel as compared to the OTFS?
Let me see. What do you mean? I think they should. I think we should have the same channel, Jun, and because if we look at this, modeled channel, this modeled channel only consider and your physical channel after we do sampling. If we do the sampling with same bandwidth, that means we have the same delay resolution. We have the same frame size, that means we have the same Doppler resolution. We will see the same channel.
Sorry, I just want to add a word.
Yeah, please.
This kind of channel delay resolution depends on your receiver filter. So yeah, after the receiver filter, you do resampling. So you see the equivalent channel is a combination of the transmitter filter, physical channel, and the receiver filter. So if you use different filter, they may cause a different equivalent channel.
ODDM 我就听不太懂了，我再跑学。
So that's my answer to your questions. If you use different filter, you see different channel. But
okay,
Thank
eventually,
you very much.
You will see the on the grid channel because you are performing sampling.
Yeah.
Thanks a lot.
Okay. Oh, okay. Thanks for the answer. And we still get several questions, but due to that limitation, maybe we do not have time to ask the speakers during the seminar. So if you have any further question, maybe you can drop email to Professor Yuan and Professor Lin. Okay. So thank you very much, Professor Yuan and Professor Lin. Thanks for the interesting talk.
Thank you.
Okay, thank you very much. Yeah, we would be happy to answer the questions by email. Bye.
Bye.
Okay. Okay, thanks. So next we're gonna have another talk from Nuria. So Nuria, are you here?
Hi, how are you?
Oh, hi. Hi, yeah. So before we start, just let me introduce the speaker. So let me share my screen first. Okay, so we're gonna have another talk from Professor Nuria González Prelcic. So she received her PhD in electrical engineering in 2000 from University of Vigo, Spain. She joined the faculty at NC State as an associate professor in 2020. She was previously an associate professor in the signal theory and the communications department at the University of Vigo, Spain, and also held visiting positions at the University of Texas at Austin and the University of New Mexico. She was also the founding director of the Atlantic Research Center for Information and Communication Technologies at the University of Vigo. She is an editor for IEEE Transactions on Communications. She is an elected member of the IEEE Sensor Array and the Multi-Channel Technical Committee and the IEEE Single Processing for Communications and Networking Technical Committee. She is a member of the IEEE SPS Integrated Sensing and Communication Technical Working Group. Her main research interests include the single processing theory and the single processing and the machine learning for wireless communications, filter banks, compressive sampling and estimation, multi-carrier modulation, massive MIMO processing for millimeter wave, V2X, A2X, and LEO satellite communications. She is also interested in joint localization and communication, joint radar and communication, and sensor-assisted communication. She has published more than 120 papers in the topic of single processing for millimeter wave communications, including a highly cited tutorial published in the IEEE Journal of Selected Topics in Signal Processing, which has received the 2020 IEEE SPS Donald G. Fink Overview Paper Award. Okay, so without further ado, let's welcome Professor Nuria to give us an interesting talk on sensor-aided communication and communication-aided sensing. Okay, so I will stop my sharing. So Nuria, could you please share your screen? Thanks.
Yeah. Thank you for the introduction. It's very nice. Thank you also for the kind invitation to give this talk, where I will try to give you my perspective on these two problems of sensor-aided communication and communication-aided sensing, and the different signal processing and machine learning tools that we can use to solve the different challenges. Let me wait. I guess it's okay. Okay. So we are working with this concept of future integrated sensing and communication networks, where we will be able to consider the information coming from the different sensors that are in the devices in the network, also the sensing capabilities of the radio communication itself. And we can use all this information to also enhance the network operation. So we are considering this integrated view, and I like particularly this word integrating, because it's not about joint sensing and communication capabilities only. It's also about integrating all the sensing capabilities in the network that can be in the sensors in the devices. A clear example is a vehicle with all the cameras, radar, LiDAR, and also sensors that we can install in a base station, in an access point. And of course, the wireless sensing capability. And all this information can give you, can give the network a map of potential blockers of users that can be used to really manage and enhance the operation of this network in terms of adaptation to the changes in the environment, to blockage and many other events. So I'm going to talk about these two types of interaction between sensing and communication, how to use the sensing information to help communication, for example, for reconfiguring the link after a blockage event, or just for initial access. And how can we use, what can we do to enable the sensing capability of the communication waveform? And I'm going to focus on millimeter wave communication, because in this case, the sensing capabilities are higher, obviously, because we are operating at higher frequencies, higher bandwidth with larger arrays. And this gives us much better angular resolvability, delay resolvability that is useful for sensing purposes. And the applications on the user side are many, just the localization or tracking of devices, but also gesture and activity recognition, for example. So I will talk about the work that has been done and is being done right now in my group, mainly by 3 members in my team, Jun, Murat, and Yuan. And we are working on the different problems: joint localization and communication, race-aided localization, sensor-aided communication. We are working in indoor environments, vehicular environments. And well, I hope you enjoy the approaches that I'm going to explain today. I will start with the problem of joint localization and communication on millimeter wave. I will describe the work that we have been doing funded by Toyota and Samsung mainly. So in this case, we focus on the ability of the communication waveform to sense, to locate objects in the environment, but these are connected objects. We are going to use either the downlink signal or the uplink signal. The devices, the objects have a transceiver, and the receive signal at the transceiver in the object, in the device, or the transceiver in the base station, it can be used to somehow obtain the position of the device. It's a byproduct of the communication system. And there are many approaches already that are being published, in the few years, the last years. But the performance that many use cases in 6G or even in Wi-Fi networks are being expected by industry really go very, very far. It's very difficult to obtain a localization error of 1 centimeter in an indoor scenario. It seems that it would be required for immersive reality applications, or a localization error is smaller than 10 centimeters in vehicular outdoor for some of the use cases with automated vehicles too. So what can we do to move forward to increase this localization accuracy when we use the communication waveform for this? The basic idea behind exploiting the millimeter wave signal for localization leverages the channel sparsity. So if you think about the millimeter wave channel, which is sparse, has a very few paths which are relevant. The thing is that it's very easy to establish a connection between the parameters of those paths, the delays, the angles, and the objects in the environment. It's possible to establish that geometry that give us this connection between channel parameters, as you can see here, and the location of scatterers and devices in the network. If you think only, for example, in the geometry, in the geometric relationships that we can exploit when we draw this triangle, if we have a line of sight path and a first order path, you can imagine that it's very easy to obtain the position of the device given the position of the base station if we know the channel parameters. I'm not gonna solve the geometric problem, but intuitively you see that it's possible to do it. And for that, we just need to have an accurate estimation of the channel. We need to know mainly the angular parameters, the direction of arrival and departure, and the delays. But in our channel model, we are working with a discrete time channel model. We are doing all this processing in digital. So we need to include filtering effects. We cannot work with delta functions here that have been used in preliminary work. We need to move forward. We need to introduce these filtering effects in a given function that can be like something similar, for example, to a raised cosine filter that is modeling that filtering that happens at the radio frequency stage in the transmitter and the receiver. And we also need to consider the clock offset. It's not realistic to think that are synchronized completely, the transmitter and the receiver, and that the channel estimation algorithm is going to give us the absolute delays. The channel estimation algorithm can only give us the relative delays. So it's possible to do this connection between position of the device and orientation of the device and the channel parameters, but we have to be realistic in our channel models and the assumptions in the methods. What are the limitations that we need to overcome? That if we want to work now on all these problems, we should be aware of? Well, one of them is this use of the oversimplified channel model without any filtering effect. So in some preliminary works, we find here that this is a delta function. That means the channel is not band limited. It's not a realistic channel model that we can use in the discrete time equivalent channel model. We also find some works where it is assumed a fully digital MIMO architecture at the device, at the base station. This is still not possible on millimeter wave if we use high resolution converters for both the transmitter and the receiver. So we need to maybe use a hybrid architecture, or if we want to use fully digital, we need to be careful about the number of bits in the converters. We cannot assume perfect synchronization. If we do that, yeah, we're gonna have very good results, but they are really fake. They do not correspond to a realistic simulation. Another problem we have is that theoretically we know, okay, if we have large arrays, we can have a very good angular resolution, resolvability. If we have a high bandwidth, we can have a very good delay resolvability. But when we operate with these large arrays, the complexity because of the number of elements also increases. And in many of the previous papers, what we find is many simulations where the authors are able to report results for relatively small arrays, like 4 by 4, 6 by 6. And that's because the complexity of estimating the channel with really large arrays, let's say 32 by 32 or 16 by 16, cannot be achieved with most of the channel estimation strategies that are being published. Another problem is when we establish that geometric relationship that you can see here between the channel parameters and the positions, we need to know the order of the path. We mainly need for localization the line of sight path and the first order reflections. The other reflections, second order reflections, third order reflections are not useful for localization in general. They are going to be very weak. So we need to not only estimate the channel parameters and the parameters for all the paths, we need to know, okay, this path is first order reflection, I can use it for localization. If we don't do that, then we are going to use in that geometric relationship some values that are going to distort completely the estimated position. And another problem that I can see in previous work is the simplistic simulation scenarios, very synthetic, completely synthetic scenarios in many cases. And well, I know it's difficult to have experimental results with real hardware and everything, but I think in the middle, we can try to do some ray tracing, for example, as I will explain later, to add some realism to our simulations. And of course, this is a new area, and of course, the preliminary work has to start from an initial step, where we are now trying to add more realism, more practical considerations. And my critic here for previous work is just a way to try to define strategies to go farther, to move forward, to be able to operate in realistic scenarios. But of course, the initial contributions were great because we're establishing the way of doing things and the main ideas behind the methods that I'm going to explain today here. The approach that I would like to explain, following the title of the talk, combines machine learning and signal processing. I do believe that there are some problems that are better addressed with a model because the model has been validated extensively over the years and it works very well. So we need to exploit it. We know it. It's gonna give us a better solution than if we just try to use machine learning for everything. However, there are other problems that are more difficult to address with a model. And in that case, I think data-driven approaches can play a very interesting role. So in the talk today, I'm gonna describe better ways to do compressive channel estimation in the sense of reducing complexity so we can operate with really large arrays and in two dimensions like planar arrays, not just linear. And I'm going to explain an approach to classify the paths that are estimated in line of sight, first order, or higher order. And with that information, we will be able to apply a given geometric transformation that depends on if the channel is line of sight or doesn't have the line of sight component. And then we can obtain an estimate of the position. And we can further use other machine learning approaches to refine that position estimation. And I will try to explain the contributions here and the ways we found to build upon the previous strategies and increase the accuracy of our estimations. I need to explain to you a little bit the channel model that is the basis for the localization. And this is a model in the time domain. So I have a matrix HD, a MIMO channel matrix. The index D is the delay index. So we have a filter, and every tab in the filter is a matrix because we need to establish the connection between the antennas at the transmitter, the antennas and the receiver. And we have several tabs, as you can see here. And for every tab, the channel matrix has the path gains, has the antenna array responses evaluated at the angle of arrival for the receiver and the angle of departure for the transmitted array steering vector. And we have a time response that models those filtering effects, those filtering operations that happen at the transmitter and at the receiver, and later at the receiver in the discrete time stage, in the digital stage. I have an equivalent function that is modeling all that. And I have the clock offset there, I have the delays, and well, this is the model that has been extensively validated, and maybe it's an interesting idea to keep exploiting it. This matrix HD can be also written in this compact form, where I have a channel matrix AR that, sorry, a channel matrix, no, what we call the steering vectors are in this matrix AR, the steering vectors for the receiver evaluated on the angle of arrival, and in this matrix AT, I have the steering vectors for the transmitter evaluated in the directions of departure. And this diagonal matrix contains the path gains with the impact of the filtering and the delays and clock offset, right? It's like sampling that equivalent waveform that we are having in discrete time. And well, we want to exploit that the millimeter wave channel is sparse, that there are a few paths that are relevant, and those paths are grouped in the angular domain. We have clusters in the angular domain for the angle of arrival and for the angle of departure, and we have clusters in the delay domain. So we need to write a sparse expression for this matrix HD. If we just look at this, we don't see that the channel is sparse anywhere. So we need to first try to write the sparse representation of the channel. To do that, one way to do it is to vectorize the channel matrix. So I can just create this vector where I'm vectorizing the channel matrix for the first tab, the channel matrix for the second tab, and so on. And well, then I can write that vectorized channel matrix this way, where I have the Carteret route product of the matrices that contain the steering vectors evaluated on the actual directions for the transmitter and the receiver. And here I have the channel gains with the impact of the filtering function, as you can see here in this vector gamma. Still no sparse expression here that we can see. So we need to work on that. How can we represent the sparsity in the angular domain? So we have this initial vector, is the same as here. And we are going to transform this in a way that instead of working with the steering vectors here and steering vectors here evaluated on the actual directions of departure and arrival, I will a much bigger matrix where I put many possible directions of departure here and many possible directions of arrival here. I don't have the actual directions anymore here in these matrices, but just the steering vectors evaluated on many possible directions. And this vector, because I have done that, this vector is going to have many zeros, because in this one, I only have the gains corresponding to the actual directions that are appearing in the channel. Here, I'm adding many possible directions, but for those directions, I don't have any path. So in the corresponding gain, I will have a zero. So this vector is sparse. And this is the way I have to create a sparse representation for the channel. I have used dictionaries in this case in the angular domain. And I can also introduce an additional dictionary in the delay domain to represent the sparsity in the delay domain. If you look at this expression for XTD, it's going to depend on this filtering function and the path gains evaluated with these delays. But that we have a sparsity in the delay domain, I can also build a dictionary for this part of the channel model. I can also build a dictionary for that. And I can further represent that vector hat XD as a dictionary for the delay domain multiplied by another sparse vector, which is now even more sparse than before. So basically, I'm gonna work with this model here for the channel, where I have steering vectors evaluated on a grid for the transmitter and receiver, and where I have an evaluation of the pulse shaping function for different delays. And here I'm considering the clock offset too. With this model, I need to create a measurement of the channel, and I need to reconstruct the channel from that model. So to build the measurement, what I'm gonna do is to send a sequence of training symbols. In this case, I'm using the notation M for the training frame for the nth interval. So I have many training frames. I send several symbols and symbols per training frame. And those symbols go through the precoder, FRF, and then they go through the channel, and then I receive them through the combiner. And I'm considering a hybrid architecture here. So I'm being more realistic here because I'm considering a hybrid architecture. This is not all digital. This means that this precoder and this combiner cannot be anything that works well for me, that works well for localization, because I have the hardware constraints there. So I need to be careful when I decide this precoder and this combiner. And there are works that try to optimize that, but we need to do it considering a hybrid architecture. This way, just collecting the receipt signal for different training frames, I can collect an observation of the channel that you can see here in this expression. And my goal is to write that observation of the channel as a sparse recovery problem. So I need to write that observation in terms of a sensing matrix, a dictionary, and a sparse vector. This sparse vector, we already said that has many zeros, and in the non-zero coefficients has the path gains multiplied by the effect of the filtering function. And well, we can also find expressions for that dictionaries that we have here. And we can see that the dictionary is, the details are in this paper on the bottom of the slide of the derivation of the dictionary, but it's quite straightforward to find the expression for this as a function of those steering vectors evaluated in a grid for the transmitter, for the receiver, and also the dictionary for the delay domain, which is the evaluation of the pulse shaping filter that we are using. And you can see that we are reading the dictionary as a Kronecker product. And well, that's going to be a problem because when we use the Kronecker product, we are increasing the dimensions of the matrices that we have here. And for the sensing matrix, basically what we are saying is that to measure the channel, we need some precoders, some combiners, and we are training with different precoders and combiners, the different frames, and we are sending different symbols. And that's my sensing matrix. So I can write a compressed sensing problem, a sparse recovery problem, where I have an observation, which is the received signal for different frames, and I have a sensing matrix that depends on the training precoders and combiners and the training sequence, and a sparsifying dictionary that is this Kronecker product and the vectorized channel, right, for all the delay tags. The problem is that when we want to use the channel estimation stage for localization, we are going to need to use planar arrays. That means a large number of antennas. We are going to use much more dictionaries with a finer grid for localization and for channel estimation. For channel estimation for communications, if the only goal is to steer the beam, the resolution that we need in these dictionaries for the steering vectors is not that big. Maybe it's enough with twice the number of antennas or 4 times the number of antennas, but maybe that resolution for localization is not enough. If I only have 16 antennas, working with a grid that is only 32 for the angular domain is not enough for localization. It's going to introduce an error in the angular domain that is not going to give me that expected performance on 1 centimeter indoor, 10 centimeters outdoor. So you can see here that the problem is the dimensions of these methods that I need to create. The dimensions become very big when I try to use large arrays, say 16 by 16, 32 by 32. This is just impossible. The memory requirements and the runtime requirements of these are impossible. The current algorithms cannot work. So what we are proposing to solve this limitation, what we are proposing is to use a new algorithm that we have been developing that works with a multidimensional dictionary. So we never built anymore this Kronecker structure where we are increasing and increasing the size of the dictionary. We work instead with a product of dictionaries. And this product of dictionaries contains the dictionaries for the different sparse domains in our problem. In our problem, the sparse domain is the angular dimension in the angle of arrival and here, and the angular dimension in the angle of departure. And those sparse dimensions are independent. I can have intuitively independent dictionaries. I don't have to build a single one that has everything together, all the sparse components there integrated. Just working with these smaller dictionaries, independent dictionaries, in this case, for the channel estimation problem, I need 5 dictionaries if I work with a planar array, because I have 2 dimensions. So I have the 2 dimensions for the uniform planar array for the angle of arrival, 2 dimensions for the planar array for the angle of departure, and then the dictionary for the delay, which is just 1. So if I operate with those 5 dictionaries, I can really reduce complexity a lot, but I need to solve a different sparse recovery problem. This problem, where I have a product of dictionaries, has not been solved before in the literature of compressed sensing. So we had to work on finding a suitable algorithm to solve this kind of a sparse problem with multidimensional dictionaries. Now we have some solutions, and it's in this paper that is under review now. I will make it available in archive today, also the code. And you can play with it. I think it's an interesting solution to reduce complexity. And in the paper, you can see how this algorithm can work in many situations with many realistic parameters for the number of antennas in the arrays that where the other algorithms just cannot run. Well, I'm going to skip the details of the algorithm in the interest of time. What other assumptions we need to drop? Well, the other assumption we need to drop is the perfect synchronization. In many preliminary works, we have to just consider that this clock offset is 0, because just to start with, to solve the problem, we make assumptions, and one of them that was done in the beginning is considering that there is no clock offset. So in that case, obviously, the channel estimation algorithm is going to give me the absolute delay of the line of sight component. In a real system, that's not going to happen. The channel estimation algorithm is going to give me the relative delay with respect to that clock offset. So I need to exploit geometric relationship that leverage these relative delays, or I need to include as a new parameter in the estimation the clock offset as well. And well, we can establish many different geometric relationships. We can exploit many different trigonometric properties here to establish these relationships, but we need to be careful. We need to know that the channel estimation algorithm is giving us this relative delay. This is an example of localization without perfect synchronization assumption, where I exploit some geometry that appears in indoor channels, and that helps me to find a way to estimate this clock offset too. In this case, what we are going to do is just to think that if I have an indoor environment with walls and floors and a floor and the ceiling, I can exploit that the line of sight, a path like this one, is going to travel the same horizontal distance as a first order reflection on the ceiling or on the floor. So let's say the horizontal distance, which can be computed like this for any possible first order reflection in terms of the direction of arrival in the x-axis and the direction of arrival in the y-axis. This is the distance that I travel on the horizontal axis, and is the same for all the first order reflections and for the line of sight path. So I can establish this kind of equation, and I can do something similar with the walls. If I have a first order reflection with a wall, this travels the same distance in vertical as the first order, as the line of sight. And I can establish this other relationship. And finally, if I write this kind of equation for all the paths that I have been able to estimate, I can find the clock offset that best matches all my measurements of the relative delays. And once I have the clock offset solving these equations here, I can compute the position of the mobile using some simple geometry like this. If I know in this case, the mobile station is the transmitter, is an uplink, I know the position of the base station, which is the receiver. C tau 1 is the distance for the line of sight path, and theta 1 is the angle of arrival for the line of sight path. And if I know the delay provided by the channel estimation algorithm and the clock offset, I can solve this and obtain the position of the mobile station in this case. But you can see that I'm only using first order reflections on the line of sight for localization. So I really need this path classification strategy. The solution that we have for looking at the channel parameters and deciding if it's line of sight, if it's a first order reflection or high order reflection, is a data-driven approach. And it's important that we do this because if we use in this kind of, you can imagine that if we use here a path, which is second order, third order, and we use the parameters here and establish this equation, we are going to distort completely our solution. It's very sensitive, our localization problem, to having a path that we are treating as first order when we write this equation, and then it's not, because then this equation doesn't have to be fulfilled for that path anymore. So we need to be careful about doing that in the right way and being very accurate with that. We developed this simple network. It's nothing complicated. It's a deep network, but it's simple. It has fully connected layers. It has a leaky ReLU. And you see it doesn't have many layers either. And with this kind of network, the localization accuracy that we can obtain in the classification of the channel paths is in the order of 99% in a vehicular setting with realistic vehicular channels obtained by ray tracing. And here we can also see some examples of the localization error that we can obtain for the 50 best percent of the users, 50% of best of the users, 80 best percent of the users, and 95. Well, you can see that for 50% of the users, when we use the path classification strategy with this 8x8 array at the vehicle and 16x16 at the base station, we can obtain some meter accuracy, but we are not yet obtaining these 10 centimeters that is expected. So more work is needed. We have been very realistic in the simulation. In these simulations I was showing, we are trying to use ray tracing for all these. You can see an example of vehicular channel here. You can see that it's really challenging. Many of the no line of sight paths are much weaker than the line of sight path. And for localization, we need several paths. We cannot just do it with just one. So it's important that we operate with these realistic channels to understand well the limitations of our algorithm. So maybe if I run this same algorithm that I was presenting, or this group of algorithms with more synthetic channels, of course, maybe I can get 1 centimeter accuracy, but I want to do it with channels that are really challenging for me, are close to practical at least. It's possible to also simulate in ray tracing very realistic indoor environments. We have also run simulations with a very realistic home office where we have tables, we have a person, we have different elements in an indoor setting. And what we do is we generate with Omni antennas all the possible paths, and then later in a Python or MATLAB simulation, we can play with different antenna arrays, hardware impairments, filtering effects, but the channel paths, the gains, the delays, the angles, those are generated electromagnetically in this ray tracing simulation. And these are some results of those algorithms that I was presenting before. You can see here, for example, that with traditional OMP, orthogonal matching pursuit, we can only run the algorithm with a 6x6 access point. Larger arrays lead to a problem that cannot be solved in a reasonable running time, and also memory requirements that we cannot meet. And with the new algorithm, we are able to operate with larger arrays that we need for localization. It's not that like super high. It's just 8x8, 10x10 at the access point. And in that case, we can see how the localization accuracy can be improved. Here you can see, for example, how we can have a very interesting localization accuracy in the indoor environment in the order of 30 centimeters error for 50% of the users. What can we do to move forward in the accuracy? Well, we can keep working on trying to work with more accurate channel estimation algorithms. That's one research line. And another research line that we are pursuing right now is to try to refine that position. So with a model, we have been able to achieve a given localization, an estimation of the position of the device. And now using machine learning, we are trying to refine that, that position. The idea we are developing right now consists of creating a grid around the original estimate. Imagine the original estimate here. You can say, okay, I'm going to consider another possible position, 10 centimeters left, 10 centimeters up, another one here, another one here. Those possible positions around on the tiles center around those points in a grid. And we treat the machine learning problem of giving a probability to all these tiles around the initial estimation. And we can design and train a network that gives us the probability of this being the true tile for the position of the device and not this. And the idea is that we get those probabilities and we choose the tile that has the highest probability. I'm not going to give the details yet about how we do this, but the results that we are having are very promising. These are examples where we are using a 5x5 grid around the original position that is marked here with this pin. So the channel estimation plus path classification algorithm is giving us these points in the center of the grid for these different cases. And we train our network and we are able to obtain probabilities for the tiles around. And well, in this case, we are able to go from a localization error of 40 centimeters to 16 centimeters only for this example, and 40 centimeters to 14 centimeters for this other example. These are just examples. We are working on the final version of the paper and we will be ready soon. You will be able to see the details and more detailed simulations. But I just wanted to identify another possibility to use machine learning to increase the localization accuracy. We can also use RIS to increase the localization accuracy. I think RIS is super promising for high accuracy localization. Why? Because it's giving us that additional strong path. We have the regular millimeter wave channel, a line of sight path, maybe some non-line of sight path. And here we have a very strong, compared to the non-line of sight path, additional paths that give us very good information for localization. So it is possible to now try to estimate that overall channel that has the base station, mobile station channel, plus the base station RIS mobile station channel. But well, we are not going to go through the details because we don't have time, but this is just to give you an idea that the channel is much more complicated now. And we need to estimate the whole channel if we want to exploit both paths, the ones that we are obtaining via the RIS and the ones corresponding to the conventional millimeter wave channel or direct channel. So we can also use this sparse recovery algorithm, MOMP, that I was describing before, to estimate these composite channels, where now the problem is even more complicated because the dimension of the RIS is also high. We need to work with a RIS that is not small in the terms of the number of elements, can be at least 16 by 16, 32 by 32. So this is complicating a lot the sparse recovery problem. But you can see here the huge gains that we can obtain just by using RIS. You can see this black curve correspond to using the paths coming from the base station directly and from the RIS with 32 by 32 RIS in one case, in the continuous line, and 16 by 16 RIS. And you can see like 90% of the users have a very, very small localization accuracy. 50% of the users maybe are below 30 centimeters, which is really much better than what we can obtain without the RIS. So RIS is a very promising also technology to increase localization accuracy. We need to keep working on reducing complexity of the model-based channel estimation algorithms. And we need to ask ourselves if the machine learning approaches that are being defined for channel estimation really provide an advantage over model-based strategies. I have not really seen it. So far, I think the model-based approaches are super powerful for channel estimation. And maybe this hybrid idea of combining machine learning is solved for some of the tasks, but still exploiting the model for the channel is interesting. And of course, we need much more work on reshaded geolocalization and communication. I will try to give now an introduction to the problem of radar-aided communication. So now we have defined a tool to obtain position information. There are other ways to obtain position information, as I said before. That can be the sensors in the devices in the network, vehicular sensors, for example. And we want to exploit that information, sensing information, to help the network configuration in this part of the presentation. Why do we want to do that? Well, because the array configuration in millimeter wave system is taking a lot of the time of the system and is reducing the rate that we can achieve. In these measurements with commercial 5G hardware, just because when we have blockage and we have to resort to a non-line of sight path and do the reconfiguration again, we are losing a precious time to some data that we are using to reconfigure with this beam training strategy. And the beam training strategy in the standard is quite painful in this sense. It takes a lot of time. You have an example here using a 64 antennas base station with an analog architecture and a user with 16 antennas. We are going to need more than 300 milliseconds for initial access. And that reduces the average rate that we can get because we are using too much time on configuring the arrays. So what can we do to reduce that configuration time? And one idea is sensor-aided communication. Sensor-aided communication is okay. The sensors at millimeter wave, for the millimeter wave channel can be related to the channels for the sensors can be related in many cases to the millimeter wave communication channel, just exactly because of this sparse structure, this idea of having very few paths that can be related to the scatterers in the environment. A radar can also observe that behavior because it's going to be operating at similar frequencies. For example, the millimeter wave radar in the vehicles. It's also operating at 77 gigas in commercial vehicles. It is observing a channel that is very similar to the communication channel. And we could use, for example, that information to extract some initial information about the millimeter wave channel and reduce a lot the channel estimation time. We tried this idea with two different approaches, an active approach where a radar at the base station line of sight channel is trying to use that information of the vehicle that can be sensed from the base station with that radar to configure their millimeter wave array for communication here. And we also use a passive approach where we are just listening to the automotive radar in the vehicle to understand the radar channel between the vehicle and the base station and use that information to configure the millimeter wave link. We tried initially this approach in ray tracing. We also built a prototype, and these field measurements correspond to the azimuth power spectrum of the communication signal in blue and the radar signal in red. Of course, this is a prototype, it's a control environment where we do not have more interference. It's just the vehicle and the base station here. But we observe this similarity in the azimuth power spectrum here. And this is what we want to exploit. Basically, what we are saying is that directions of departure and arrival for the radar and for the communication module are going to be similar. So we have an initial guess that is coming from radar that we obtain for free and that we can later refine. Yeah, no one is stopping us from refining that, but we don't have to start from scratch. We can start from here, and that's a lot of information. In this passive approach to exploit the similarity between radar and communication channels, we consider that we have the collocated arrays at the base station on the road. And we consider that the radar in the vehicle is an automotive radar operating at the used 1 millimeter wave frequency. And we are going to consider the same number of antennas in radar and communication array to simplify the maths and the initial developments. And in that case, what we did can be summarized in this kind of approach. Listening to automotive radar signal, here at the base station, we listen to the paths that are coming from the automotive radar. We can estimate the radar covariance, right? Here, we can estimate the radar covariance just by listening to the radar signal. And then we can try to map the radar covariance to the communication covariance, and can be two different things. We can estimate the radar covariance and try to obtain the communication covariance, or we can just try to obtain the covariance eigenvectors, because those are the ones that are going to define the precoders at the base station to establish the link with the vehicle. Or, well, or we can try to define only, for example, the communication azimuth power spectrum from the radar power spectrum that is related with a Fourier transform to the radar covariance. So we try all these different ideas to further improve the ability of the radar covariance estimation, providing useful information to configure the link. I'm going to skip some of the details. We did a very realistic simulation. We followed the methodology that 3GPP established for vehicular channels in terms of the number of lane widths, the number of car, the car and truck ratios, the intervehicle distance, all these parameters in the traffic and the streets that are defined by 3GPP for realistic vehicular communications. And we created our ray tracing channels for this case. And to simulate the radar, we just simulated an Audi A8 because there is not any standardized procedure. And well, you can see here some of the results. In red, you can see the rate that we can achieve with the radar-aided strategy without any refinement using machine learning. So it would be like using the radar covariance that we have here without this learning-based approach, the second stage. Just using the radar, we can obtain an overhead reduction of 77% with respect to exhaustive search. And we can also perform much better than if we just use the location information of the vehicle, even if it's perfect, if we assume that it's perfect. So that's very promising, that approach. And later, what we did is to add that machine learning-based stage where we try to learn these mismatches between the radar and communication channel. The channels are not exactly the same because the frequency is a bit different. We can use a millimeter wave frequency for communication that can be maybe 70, 68, 73, and the radar operating at millimeter wave is going to be 77 gigas. So we have that difference. We have also that the module for communication is not located exactly at the same point as the automotive radar. So there are these mismatches between radar and communication channels. And we designed these different deep networks to map this radar covariance information into different functions for communications, azimuth power spectrum or the main eigenvectors, etc. And this is, for example, the network that we designed to map the radar azimuth power spectrum into the communication azimuth power spectrum. It's a simple network again. 1D convolutional layer, leaky ReLU, max pooling, and pooling is very simple. You can see it here. And these are some examples of the performance. In blue, you can see the true radar azimuth power spectrum. In orange, the true communication azimuth power spectrum. And in green, what we can predict from radar. In this case, you can see here the prediction from radar is completely aligned with the true communication, right? So this is going to work very well. In this other case, there is still a misalignment between where the angular information is stronger, but is this peak This is what the radar is predicting, but the true communication is here. So predicted results were good in general, but with high probability, but there were some misaligned predictions, as this one you can see here. So that's the reason why we try a different method to map the radar information into communication information, and we designed a different network where we were using to map the eigenvector of the radar covariance to the eigenvector of the communication covariance. And we just use later eigenbeamforming for establishing the link. And well, in that case, it was working much better. We did very realistic simulations in terms of the parameters, number for antennas, transmit power. And you can see the results here. In red is exhaustive search. So you can see that the rate you can achieve is much worse than the one you can achieve with other strategies. In blue is the radar-assisted search without learning. I just use directly the radar information for the covariance. And that means I have an initial idea about the main directions for communication. I don't do any learning. I don't refine anything. I just use the radar info as I'm obtaining it. And what happens is I can reduce the size of the codebook that I'm using for beam training. So I can increase a lot the rate with respect to exhaustive search. And then in purple and green, you can see what happens when on the top of the radar, I introduce that machine learning stage to further increase the accuracy of the mapping between radar and communication metrics. And well, with the purple, which is basically mapping the covariance vector directly, not the azimuth power spectrum, not the eigenvector, but the covariance vector, we have the best behavior. And in this other plot, you can see similar results comparing the performance. In summary, we were able to increase the rate by 13.3 and 21.9 using the azimuth power spectrum and the covariance eigenvector translation. This on the top of what we achieved before. So this improvement, 21% is over the blue curve, which is radar assisted without learning. So this is very promising, and we have been working also on extending this to multi-user environments. We have a solution where we combine again signal processing to separate the contributions coming from different vehicles. We can do this very, very well. And then we use machine learning again to map the covariance information as I described. And these are just results for the multi-user case, where we can see the simulations when we have 4 vehicles on the road that simultaneously are trying to establish the link, which is not something that is going to happen very often, but we wanted to consider this worst case. Using this radar information, we were able to reduce the beam search size to 12 beams. So we don't do the beam training over the whole codebook, just the 12 beams around the ones suggested by radar. That's what we are seeing here. Jumping all the time. And well, I think the results are very promising. These are our initial works on these ideas. And of course, we can extend these approaches to beam tracking, not only to initial access, but also to beam tracking. We can leverage other sensors. We have other works where we have leveraged LiDAR. We can work on transfer learning. We also have some works on that, how to transfer this knowledge about how to map radar and communication from one side to another. We can also go further and not only think of beam training, but also a more complete channel estimation aided by radar. And these are the different works that we are doing in my group in 6GNC, our Center for Developing 6G Technologies at NC State. And I hope you found this interesting. And well, if you have any questions, I can answer now.
Okay, thank you very much, Professor Nuria, for your interesting talk. So we got several questions. So maybe I will ask them. So the first, actually, we have 2 questions from Ahmed Bazi. So I will ask the questions one by one. the first question is concerning the clock offset. So that might shift the delay estimates. So the question is, could it make sense to model the clock offset as a random number and embed algorithms that are aware of the statistics of that random time offset?
Well, the clock offset is in fact a random variable, but once we are fixing a given transmission and reception, it's having a given value, right? So yeah, we can adopt a deterministic approach to estimate a channel and consider the clock offset an additional deterministic parameter that is deterministic for those realizations. It's not going to be changing from one frame to the next one, from one symbol to the next one. And that's what we did. I'm not sure how to do this from a statistical perspective. We have maybe for the problem of being tracking, but I'm not really sure how to do it. I'm not going to say that cannot be done, but maybe it's different. Maybe it can be included in a different framework for channel estimation. In this one, based on sparse recovery, I don't think it's worth to consider a random approach for the clock offsets. Maybe I'm wrong.
Okay, so the second question is, how do you estimate the number of passes, L?
So when you have a given type of channel, imagine you are in a vehicular environment, you are in a home office, you know more or less the number of channels. You don't need to be accurate in estimating all possible channel in the path. All possible paths in the channel, because you only need to have some really good and as strong as possible paths. So for localization, it's okay if you say, I'm going to estimate 5 paths in the channel, even if there are 10, because those last 5 paths are going to be weaker, and maybe it's better not to use them for localization. And in any case, maybe they are higher order. So what we do to solve that problem in practice, when we don't know the number of paths, is we establish a number and we consider that that's the number of paths. And if we estimate one of the paths with a very, very, very low gain, then we discard that path for localization. It's not going to be useful. And in some cases, in the results that I show, I didn't remove the results for the devices that are far and we cannot really estimate where the channel and SNR is bad. So in that average, we have bad channels where, you know, all the paths in the channel are really bad and we cannot do the localization, for example. And establishing the link, maybe we can do it, but with a low rate because the channel estimates.
Okay. So Aman, so I hope this answers your question.
Yes, thank you very much, Professor Nuria. Also a very interesting talk. Thank you very much.
Okay, so the other question is from Carlson Fang. Okay, so thanks for the good talk. In the one-dimensional dictionary, we use familiar colloquial product, which implies the transmit and receive dimension are independent. So can you give us a intuitive explanation about the multi-dimensional dictionary?
Yeah, the multidimensional dictionary just tries to give a solution to the complexity problem that involves working with a dictionary for sparse reconstruction, where I built it introducing the sparsity in the angle of arrival, the sparsity in the angle of departure, and the sparsity in the delay domain. So when I do that, I create that equivalent dictionary, equivalent measurement matrix that is built from Kronecker products. And it's built of Kronecker products because I'm writing the signal model like that, but it's not the only way, right? So what I'm proposing is to still dealing with all those sparse components, angular domain, arrival and departure, and delay domain. Because I use planar arrays, I have 2 dimensions for the angles, X and Y. So I need 5 dictionaries. But instead of now put those dictionaries all together and build with Kronecker products the equivalent dictionary that I could just following the prior work, I'm saying, no, I don't want to write that, my receive signal like that. I want to write my channel as a product of dictionaries, and a product because that way I do not increase the size of the dictionary. I have to deal with as much smaller dictionaries, the product, element-wise product, not Kronecker product. And of course, it's complicated to write that receive signal and that channel like that, but can be done. We show it in that paper. And that helps us to solve a problem with a smaller dictionary. That's why we do it like that. It doesn't mean it cannot be done the other way. Of course it can, but results in a complexity that we cannot run the method at the end. With a 16 by 16 planar array, we cannot run it. And it is my own paper. That one I was criticizing is a paper from maybe 4 or 5 years ago. But we did the simulation with linear arrays. It was one of the initial papers on channel estimation for millimeter wave. And it was okay as an initial work. But now if we want to use this for localization, we need planar arrays, the arrays has to be large. And that algorithm is not a good solution for this. It just doesn't run.
Okay, thanks. So these are the questions regarding the race channel estimation. Okay, so the question is, are you estimating the cascaded channel or the individual channel? If it is a former, how do the receivers have more than one, do their antennas need to have more than one antenna?
The receivers have more than one antenna in our paper. This is a paper we are going to present in SPOC next week. And we are having multiple antenna receivers. We have arrays that we simulate in the simulations is 32 by 32. So yeah, we had to address this complexity again of having to deal with the composite channel, the RIS, the base station RIS user plus base station user, because we do not want to discard it, any of them, for localization to increase accuracy. If we are gonna use the RIS, yeah, when there is blockage, we can only use the RIS, but when there's no blockage, we can use both, and that's gonna help us a lot. So we do need to estimate the overall channel.
Okay, thank you.
So my question is, so do you actually estimate the cascade channel or the individual channels? Since you have multiple antennas at the users.
We estimate the composite channel. We estimate, you mean if we are able to separate the estimation of the...
Usually when we estimate the cascade channel, we require the users to have only one antenna. So since you said that the users have multiple antennas, I was just wondering if you are estimating the cascade channel, what method are you using to estimate the cascade channel? But your answer is you're estimating the composite channel. So that's the end of my question, basically.
Yes, we are able to estimate the contributions of the two channels, if that's the question. And we do it with several antennas at the user. It goes a bit beyond what it has been published before, yes.
Okay, thank you.
Okay, thanks. So due to the time limitation, maybe we should stop here. And thank you very much, Professor Nuria, for your interesting talk and candid explanation for all the questions. Okay, so I think that's all for this seminar. And thank you very much, Professor Yuan and Professor Ning, for your interesting talk and candid support for our ETI. Okay, thank you very much.
Thank you.
Thank you, Jay, for kind
thanks.
organization. Thank you, Nuria, for interesting talk. Thank you.
Thank you all.
Thank
for
you.
being here.
Yeah,
Bye.
thanks.
Yeah.
Thanks everyone for being here. Bye bye. Thank you very much.
Thank you.